Hello guys, I hope everybody is doing well. I'm sure I'm audible. So we are going to start with problems on Bode plot. So last time we have seen an introduction to Bode plot where I have made you understand what is meant by magnitude plot, what is meant by phase plot, and also I have informed you the reason why it is called as a semi-log paper on which we plot. Okay. So just to be quick in revision, now I would like to tell you that we are going to have a Bode plot which internally consists of two plots, out of which the one is called as a magnitude plot, the other one is what we called as a phase plot. The given data for plotting Bode plot is always only one thing, that is loop gain. So when I say a loop gain, it is always G of S into H of S, right? Step number one. What is the step number one, guys? Step number one, we do substitute S equal to J omega. We do substitute S equal to J omega. In turn, what am I supposed to get? Wherever there is S, we just substitute equal to J omega. So what I get is G of J omega, H of J omega. Now from this G of J omega, H of J omega, I'm going to calculate two things. One is magnitude, the other one is called as phase. For magnitude, I have to take a mod, okay, of what? G of J omega, H of J omega. And of course, to have a phase, you have to calculate a phase angle. And to get the phase angle, I have to take an angle. Phase angle of what? G of J omega, H of J omega. The very next step, what we do is, whatever magnitude that we get, we take a 20 log of it. So we make sure that this is, just a magnitude. What do I get is mdB, that is magnitude in decibels. And this magnitude in decibel is nothing but, it is 20 log of m. It is 20 log of m. Ultimately, since first of all, I have calculated, m. After that, I have calculated m in dB, that is magnitude in dBs. And once I have that, okay, on y-axis, I'll make sure that I have mdB. On x-axis, we have omega. Okay. And on this axis, we plot something called as a magnitude plot. Okay. Next, when I have to get a phase plot, okay, this angle is by default is in degrees. Okay. So angle of G of J omega, H of J omega, I'm going to take it on y-axis as it is. And on the x-axis, I'm going to have an omega. Okay. I hope everybody is understanding that. Okay. If you're understanding this, guys, let me know that you're understanding this. One more thing, since the magnitude are in decibels, the minimum value of magnitude in decibel would be what? 0 decibel. Then the standard values I'm taking, it is 20 decibel, then 40 decibel. Okay, I'm not writing units, but try to understand whatever figures that I'm writing on y-axis will have unit as decibels. Okay, then below 0, it would be common sense. It would be minus 20, then minus 40, and so on. Okay, and talking about x-axis, we have already discussed that the typical value that we start with the omega is 0.1. You never ever start with omega equal to 0, guys, because ultimately for calculation point of view, you'll have to take a log of omega. And if I take omega equal to 0 as a starting point, log of 0 is infinite or not defined. And that's the reason why we never ever take omega equal to 0. But yes, of course, we can start with, the lesser value of omega. And again, it shouldn't be like 0.1 always. You can go for 0.001, so on. Okay. So you can take any, starting value of omega. So I'm typically starting with 0.1. Okay. The next value, okay, as you can see, it is like a normal graph, okay, where the every unit is spaced from each other of 1 centimeter. So after 0.1, we take a multiple of 10. That is, after 0.1, we take omega equal to 1, then we take omega equal to 10, then we take omega equal to 100, then omega equal to 1000, and so on. Okay, so as you can see that I'm following something called as a logarithmic scale. I'm following logarithmic scale, and that's the reason why I said that the x-axis happens to be what? A non-linear scale. It is a non-linear scale because you cannot define a scale. You cannot say how much is 1 centimeter. But on a contrary side, if you look at y-axis, y-axis is a linear scale. It's a linear scale where I can, y-axis I can say that 1 centimeter is always 20 decibel. So I'm able to express my scale value on y-axis, but I cannot express my scale value on x-axis because x-axis is a logarithmic scale, or it is also called as the non-linear scale. Okay, same goes for phase plot also. So on y-axis we have the minimum value as 0 degree, then let's say 90 degree over here, then 180 degree, and by common sense it would be minus 90, minus 180, and so on. But what remains on x-axis is the same scenario that we already had over here, right? So we are going to start with 0.1. On the next centimeter, I will multiply this omega by 10. It will become 1, and 1 multiplied by 10 will become 10. Then it is 100, and so on. Okay, and because of such scale, I can take large values of omega in the single graph, and that's the whole motive of using a logarithmic scale, guys. Okay. So I'm sure now you understood what I said so far, and now I'm switching to a very important things. Okay, so there are certain things that I'll tell you that you may try to remember these things, and if you remember, then it is then it become very easy for you to plot a Bode plot. And let me tell you, otherwise, if you follow a normal university method, it is going to take so much time of yours. And again, when it comes to GATE exam, as I keep saying that time is money for you guys. Okay, so you have to use it. You have to invest minimum time, and minimum time you have to solve maximum problems. Okay, and for that purpose you need to have some shortcuts with you. So let's hit on those shortcuts required. We'll try to accumulate those shortcuts together. We'll try to remember those shortcuts, and once you know those shortcuts, then we'll directly hit on the problems. Okay, and then you will see how to solve Bode plot within 2 minutes or 3 minutes at the most, and not more than that, guys. Okay, otherwise if you go for a traditional approach, that's a classical approach that we follow for a Bode plot, it takes minimum 15 to 20 minutes to solve only one problem. So guys, let's see. So what you are going to observe in the given g of s, h of s, you're going to observe two important things, that is poles and of course zeros. Poles and zeros are something that you're going to observe. Okay, for example, poles and zeros can be at origin, or they can be simple pole or simple zeros, etc. So assuming I'm talking about there are n poles or n zeros at origin. If there are n zeros at origin, then the term would be equal to s to the power n. Okay, for example, if it is s square, then it indicates there are two zeros. Okay, s square in the numerator, then it is having two zeros at origin. So s to the power n in the numerator term indicates there are n zeros at origin. Okay, so how does that contribute in a magnitude plot and phase plot? That is our concern, guys. Okay, ultimately when you have to plot a Bode plot, you need to take care of magnitude and phase. So each and every pole, each and every zero is going to contribute in magnitude plot as well as phase plot. So we have to just see the effect of poles at origin. How does that contribute? If there is a simple pole, how does that contribute in magnitude and phase? And same for zeros also. So let's see the very first case that I'm saying, that I'm claiming that there are n number of zeros at origin. So the term would be common sense, it would be s to the power n. In that case, in the magnitude plot, it contributes a slope. It contributes a slope of always minus 20. Okay, I'm so sorry, it is 0, then it is positive 20. Okay, positive 20 multiplied by n. What n indicates, guys? N indicates number of zeros at origin. So positive 20 cross n, 20 multiplied by n decibels per decade. So this much slope it is going to contribute, guys. This much slope it is going to get contributed, okay? And at the same time, if you look at the phase, then how much angle it is going to contribute is positive 90 degree multiplied by n. So this much phase it is going to contribute, and this much slope it is going to contribute in terms of magnitude plot, in terms of phase plot, it is going to contribute 90 degree times n. I hope you are getting that, okay? I hope you are getting that. Second, if you look at, 1 upon s to the power n. Now, what does that indicate? When I say only s to the power n, it indicates, n zeros at origin. Can anybody who is watching this video can tell me what is meant by 1 upon s to the power n? Come on, guys. Okay. So, 1 upon s to the power n actually indicates n poles at origin. Okay, it indicates n poles at origin. Of course, it should something called as integrators also. But in terms of Bode plot, okay, in terms of Bode plot, we are going to look after the poles and zeros that we have in a given loop gain. Okay, so in that context, I can say that there are n zeros at origin. So let's see what's the contribution in a magnitude and the phase plot, isn't it? In magnitude, it is going to contribute a slope. It is going to contribute a slope of, the moment you will see zeros, guys, the moment you will see zeros, a slope will be positive, angle will be positive. Try to remember that. 0, positive. The moment you see pole, remember negative sign. Remember negative sign. Okay. So in magnitude, what I'm going to get a negative slope. Why negative? Because now I'm talking about poles, guys. Okay, these are not zeros, guys. I'm so sorry for that. These are poles. Okay, these are poles. Okay, so there are poles at origin, n poles at origin. So slope would be minus 20 times n, decibels per decade. Is that fine? Next, when I'm saying phase, guys, in phase, the contribution will be negative of minus 90 degree cross n. I hope you are getting that. I hope you are getting that. Now, this is something I'm talking about poles and zeros, in which I'm taking the first category, that is number of poles at origin or number of zeros at origin. The third category that I'm going to talk about, simple poles and simple zeros. I'm going to talk about simple poles and simple zeros. Okay. So if you look at simple zero, it would be in the form of 1 plus st. How do we get that form? Don't worry, I'll definitely explain you guys. Okay, just now you can just see, as you can see, I have written this, in a ratio form. If you see, it is written in the form of what? In the form of ratio. So it is present in the numerator. Something that is present in numerator as polynomial always gives you what? 0 or pole. Of course it gives you 0. And on top of that, if I write n, it indicates there are n zeros. There are n zeros, not at origin. So I can say there are n, finite zeros. There are n finite zeros, or I can say, simple zeros. So these are n simple zeros, guys. N simple zeros. Again, it is going to contribute the same, guys. Nothing differs over here. Nothing is going to differ over here. Check it out. Check it out. For zeros, what do we say? Positive sign. For poles, we say negative sign. So for zeros, we say that you get positive 20 multiplied by n decibel per decade. So here I'm going to just copy paste the same thing, guys. See, there is nothing to remember. And again for phase, I'm going to copy paste the same thing, that it is going to contribute, 90 degree multiplied by n. Okay. Now this is regarding, zeros. This is regarding zeros, guys. The fourth and the last category that we have to see is, poles. So obviously this kind of term would be there in the denominator, 1 plus st term. Again, I'll definitely explain you how to get 1 plus st term or 1 plus st term. I'll definitely explain you that. So what does that indicate? Something in the denominator, okay? When you have a polynomial of s, guys, in the denominator, it indicates, it contributes what poles, okay? But on top of that, if you are write n, it indicates, there are n simple poles. There are n simple poles, guys. For example, if this n happens to be 2, okay, then I would say there are 2 simple poles and so on. Again, it is going to contribute in magnitude and phase. So in terms of magnitude, again, a scenario will not be different, guys. Look at the second case. If you remember, there are n poles, whether they are at origin or whether they are, simple poles, I mean non-zero poles, still the contribution for magnitude and phase remains same. So what does that indicate? That magnitude would be same, that is, minus 20 multiplied by n decibel per decade, and the phase would be again same, that is minus 90 degree multiplied by n. N indicates a number. For example, if that n happens to be 2, as I said, it would be what, minus 180 degree, and this would be minus 40 decibel per decade. So I hope you are getting that. Okay, I hope you are getting that. If you're understanding, guys, it is appreciated that if you acknowledge me. If you're understanding this, guys, you can definitely acknowledge me. Else, of course, I'm going to move ahead, guys. So those who are watching and understanding these things, you can just tell me that you are understanding that. Okay, great, Aniket. So I'm just going next, guys. I'm just going next, and I'll tell you that whatever g of s, h of s is given in the exam, you have to make sure that you convert this in a form, that is a standard form called as a time constant form. So what is meant by a time constant form? Let us understand. So if you have, g of s into h of s, this is equal to, you have to get a standard time constant form. What is a standard time constant form? I'll show you. Okay. Okay, Aniket, the reason why I'm not going to talk about a region of convergence, because this is not a Laplace transformations lecture. Okay. Region of convergence is something that is discussed in signals and systems Laplace transform topic. Okay. So the lecture that you are watching right now is the lecture is on a Bode plot. So even though I'm using a Laplace domain here, uh, we are not going to talk about the region of convergence, because it is not in the capacity of a Bode plot to discuss that topic. Okay. I hope you understood, Aniket, what I mean to say. So the g of s, h of s, you will see that, okay, it would be like this. It is k into 1 plus t1s multiplied by 1 plus t2s, and so on, so on. I don't know how many terms would be there, so I'm just putting dots over there. And in the denominator, might be you will be having s to the power n term. Again, not necessary that s to the power n term may be in the numerator also. Okay, so it is just an example I'm taking. Okay, or in the denominator you will have polynomial of s, that is 1 plus ta into s, 1 plus tb into s, and so on. Okay, so let me tell you what are t1, t2, t3, and so on. Because t3 I'm saying because there are dotted terms. So okay, it might happen there are multiple zeros. So what are t1, t2, t3, and so on? Okay, or what is ta, tb, so ta, tb, and tc? These all of them are called as time constants. All of them are called as what? Time constants. Okay, and obviously if you reverse them, okay, for example, I'm talking about 1 upon t1, 1 upon t2, 1 upon t3. What I did, can you see that I have just inversed the term, right? Similarly, if I do for this ta, tb, tc also, okay, t1, t2, t3 are time constants from the numerator. ta, tb, tc are time constants from the denominator. What I did, I'm just reversing them for some reason. I'll tell you what is the reason behind that. That is 1 upon ta, 1 upon tb, or 1 upon tc. In this case, that 1 upon time is what? Come on guys, what is 1 upon time? How simple question is that? Come on, what is 1 upon time? What is 1 upon t? Mathematically, logically, by using your common sense, which is very uncommon that I see nowadays in students. So basically, let me tell you 1 upon t is frequency. Okay. Therefore, 1 upon t is always frequency, right? So all of them gives you frequencies. And let me tell you, they are not normal frequencies. They are something called as corner frequencies. They are called as corner frequencies. So what is meant by common frequencies? Okay, corner frequencies. Okay. So corner frequencies are those frequencies at which you will see there is change in the slope of the magnitude plot. Okay. So at corner frequencies, these are considered as critical frequencies at which, because of the pole and the zero contribution, you will see the slopes are changing. You might have seen, Bode plot like this, a magnitude plot like this. You might have seen this. Okay, you might have seen this. As you can see in this Bode plot, or magnitude plot, as you can see, okay, as you can see at these 3 points, I'm talking about, okay, point number 1, point number 2, and point number 3. So at these 3 points, as you can see, the slopes are changing. Can you see that? I'm talking about these points. Okay, this is point number 1, I'm saying, this is point number 2, I'm saying, and this is point number 3. So at these 3 points, can't you see that slopes are changing? Okay, these points are called as corner frequencies. These points are called as corner frequencies. So let's see what are those corner frequencies, how to get time constant form, everything that I'm going to see, guys, everything that I'm going to teach you. But after taking an example, okay, so let me just take an example just to show you what flow we are going to have, for going for a Bode plot. Once we understand that flow, then I'll start with the problem. Okay, so let me go ahead, guys. So let us assume, g of s h of s given like this, which is 15 times s plus 2 multiplied by s plus 4 whole divided by s into s plus 3, then s plus 5, and so on. Okay, in that case, as you can see, it is not in time constant form, guys. It is not in time constant form. How do I understand that? If you remember the last time what we had over here, like k into 1 plus t1s 1 plus t2s whole divided by s to the power n. If you remember, it is 1 plus tas 1 plus tbs, and so on, guys, right? So can you see that each and every bracket, it's starting with a standard term, that is 1 plus something. Can't you see it is not like that? In order to convert it into time constant form, let me do this way. So what I'm doing is I'm just copying 15 as it is. Then let's try to convert this. Okay, so what I'll do is I'll take 2 common, guys. I'll take 2 common. If I do so, I'll take 2 common. What it would be in the bracket? 1 plus, can I say it is s by 2? 1 plus s by 2. Then I'll take 4 out. So what remains inside? 1 plus s by 4 whole divided by s as it is. Then I'll take 3 common, so as to make it 1 plus st form. So I'll take 3 common. So it is 1 plus s by 3 multiplied by 5 common again, in order to even convert this bracket into 1 plus st form. So 5, if I take common, what remains inside is 1 plus s by 5, and so on. I hope everybody has got that right. So let's solve this. I mean, try to cancel out some terms. So as you can see, 3 5s are 15. This 5 and 5 gets cancelled. 2 multiplied by 4 will become 8. So what we have in the numerator is 8. So let me again write it. You have 8 over here. Then 1 plus s by 2, 1 plus s by 4, then s as it is, s to the power 1 it is. So it is 1 plus s by 3, then 1 plus s by 5. I hope everybody got that. I hope everybody got that. Okay. And please remember, the coefficient of S is called as time constant, right? The coefficient of S, I'm talking about the time constant form, not every time, guys. Okay. So in this time constant form, coefficient of S is called as time constant. Am I right? Coefficient of S is called as time constant. What does that mean? What does that mean is, here I would say time constant is 1 by 2. Here, come on guys, time constant is what? It is 1 by 4. Here, time constant is what? Come on, it is just coefficient of S, nothing else. So I'm not, following something rocket science. Okay, it's very simple thing. It's just a common sense thing I'm talking about. So the time constant is 1 by 3, and the time constant over here is 1 by 5. So these are the time constants do I have. Okay, these are time constants, guys. Okay, from which by inversing them, you will get something called as corner frequencies. I hope you remember that. Look at the last slide once again. Can't you see? T1, T2, T3, I have inversed them. I got corner frequencies. Then TA, TB, TC were time constants, to which I have inversed to 1 upon TA, 1 upon TB, 1 upon TC. All of them indicates corner frequencies. So I'll tell you step number 1 to be followed. Once again, I'll tell you what is the step number 1 to be followed, guys. So step number one is to consider poles at zeros. I mean to say poles at origin or zeros at origin. As you can see in this example, there are poles at origin and there is only one pole at origin. So to be very precise, there is only one pole at origin. So step number 1, you have to arrange the terms like this. You'll take 1 upon S term first. Okay. So in a way, when you are starting with the Bode plot, you have to arrange them in ascending order. Okay. Or the order that I'm trying to convey you. So the first of all, you have to see if there are poles at origin or zeros at origin, consider that term very first time. Okay. So I have taken 1 upon S. Okay. Second, third, fourth, fifth. Now, how to arrange rest of the things? Okay. Now, once the pole at origin has gone, then we got, total 3 poles and 2 zeros. Okay. There are 3 poles and 2 zeros. So how to consider them? So you have to consider them in the ascending orders of corner frequencies. I repeat, in the ascending order of corner frequencies. For example, over here, what I can say, the first corner frequency that I have is, 2. Isn't it? The second corner frequency, guys, that I have is 4. Okay. I'll write CF1, that is corner frequency 1. Then CF2, that is corner frequency 2 is what? Come on, guys, it is 4. Corner frequency 3. Okay, how much it is, guys? It is 3. The corner frequency 4. It is how much? 5. Okay. So now try to arrange them in ascending sequence of corner frequencies. So if you see the minimum corner frequency, it is 2, guys. It is 2. Then I'll write that respective term first. What is that? It is 1 plus S by 2. So on the second sequence, I'll write 1 plus S by 2. Next, the next corner frequency by ascending sequence is 3. That is corner frequency 3. Then I'll write that respective term. What is that term, guys? It is not just 1 plus S by 3. It is 1 upon 1 plus S by 3. Very important, guys. The position is very important because it is in the denominator. Then I'll write the third position as 1 divided by 1 plus S by 3. Then, come on, guys. After corner frequency 3, what is the next corner frequency? Can anybody answer me? The one who is watching. Come on, guys. You have to only follow the ascending sequence, nothing else. So next ascending sequence, if you see, the corner frequency is 4, guys. Okay, which designate the 0. Okay, so it is 1 plus S by 4. 1 plus S by 4. And the last corner frequency, can you look at this? That is 5. Okay, then it belongs to pole. So I'll write as 1 upon 1 plus S by 5. I hope you understood that. So this is how I have arranged the order. Okay. So I have just taught you how to arrange the order. Still, I have not taught you how to go for a Bode plot. Okay. That is what I'm now going to start with the next problem, guys. Okay. So in first problem, what I have taught you. Okay. First step, I have taught you how to convert it into time constant form. how to get time constants. From time constants, how to get corner frequencies. And once you get corner frequencies, how to select the priority. So very first priority should be pole at origin or zero at origin. In this case, it is quite visible for you guys. There is only one pole at origin. So I'm going to always start with 1 upon s. Then rest of the terms, that is, poles and zeros terms in time constant form, you have to arrange them in the ascending sequence of corner frequencies. Okay, ascending sequence of corner frequencies. So if you remember, let me remind you once again, the corner frequency over here is 2. Then if you look at this, corner frequency is 3, guys. Here corner frequency is what? Come on guys, 4. And the last corner frequency is 5. Can't you see that I have arranged rest of the terms, in the ascending sequence of corner frequencies? Yes, of course, you can ask the doubt. Please ask me. Are you going to ask me the doubt? If you have doubt, you can type. I'll continue with my sum. So the question directly. Now draw the Bode plot. Okay, rather than suggesting me, you can ask me the doubt. Okay. So let's go for a Bode plot, guys. G of s into h of s given, guys, it is a loop gain which is equal to 10 into s cube whole divided by s plus 5 to the power 5. So for this, you have to go for a Bode plot. Amar, you can attend network theory for that. Okay. So this lecture is not meant for explaining that. So the first step is to substitute s equal to j omega. So what do I get is g of j omega into h of j omega. So wherever there is s, substitute s equal to j omega, guys. It is 10 into j omega to the power 3 whole divided by j omega plus 5 to the power 5. I hope you are getting my point. Okay. But then since it wasn't in time constant form, so I'll substitute s equal to j omega later. Okay. I can substitute s equal to j omega later. Rather, I'll not go for this step. First of all, I'll try to convert it into time constant form, guys. Okay. So how to convert it into time constant form? Very easy. Very easy. Okay. Check it out. It is 10 into s cube as it is. And in the denominator, we have 5. Okay. We want that term to be unity, guys. So what I'll do is I'll try to take 5 out. But can't you see the power is 5? So what do I take out is not 5, but 5 to the power 5. So 5 to the power 5, I'll take common. What remains inside is 1 plus s by 5 whole raised to 5. I hope you understood that, right? Great. So after solving this, 5 to the power 5, okay, 10 divided by 5 to the power 5, okay, you can just sit with the calculator. You will get the answer as 0.0032 in the numerator. Then you have s cube, and then it is whole divided by 1 plus s by 5 to the power 5, right? I hope you understood that. The next step, what you do, guys, you arrange them in the ascending sequence. If you remember the sequence that I have made you understand, that you have to first of all understand, poles at zeros or zeros at origin. Okay, I mean poles at origin or zeros at origin. In this case, there is zeros at origin, as you can see, s cube. So the very first priority that I'm going to give it s cube, right? S cube. Then I'm sure you remember, if there are 3 zeros, there are 3 zeros at origin. How does that contribute in slope, guys? How does that contribute in slope, guys? If you remember, it is 3 times 20, that is 60 decade. Please remember, s to the power n term gives you n times 20 decibel per decade, and 1 upon s to the power n introduces minus n times 20 decibel per decade. Please don't ever forget that, okay? Don't ever forget that. So this is the magnitude contribution, and then you can see the phase contribution. So phase contribution is n times 90 degree. N times 90 degree. Here n is what? It is 3, guys. So it is 3 times 90 degree. So it is 270 degree. It is 270 degree. So that is step number 1. So SQ thing is done. Now what is left, guys? Only this, that is a pole part. The pole part is left. So the left thing that I'll write is 1 upon 1 plus s by 5 to the power 5. Okay, 1 plus s by 5 to the whole power 5. So how it is going to contribute in slope, guys? So in terms of slope, it is going to contribute as minus 20 decibel times n. Minus 20 decibel times n. So it contributes minus 100 decibel per decade. Minus 100 decibel per decade, guys. Okay. So I hope you understood that. Next, guys. After slope, always try to get a net slope. Okay. I'm so sorry for that. Let me write it again. Let me write a net slope. So what is net slope, guys? Net slope is simple. Present slope plus previous slope. I repeat, present slope plus previous slope. So what is present slope, guys? It is minus 100. And what is previous slope, guys? It is positive 60. So in a way, it comes as minus 40 decibel per decade. I hope you understood that. And then we calculate something called as phase angle. So phase contribution, let us calculate phase contribution, guys. So what is a phase contribution? Very simple. Okay, it depends upon whether it is pole or zero. If it is pole, then it is minus 90 degree times n. So here n equal to how much? It is 5. So minus 5 into 90 becomes minus 40. Minus 45, 0. Okay, minus 450 degree. Minus 450 degree, yes or no? But then you also calculate a net phase angle. Again, the concept remains same, guys. The current phase plus previous phase. So what is the current phase? It is minus 450. What is the previous phase? It was 270. So minus 450 plus 270, it becomes minus 180 degree. Okay, so this much data I have, and this much data is enough for me to go for a complete Bode plot. Okay, to go for a complete Bode plot. I hope you understood that. Okay, please understand, you always calculate not only slope and phase, you calculate slope, net phase, net slope, phase, net phase angle for every term. The reason why I have not calculated net slope and net phase for a very first thing, that is SQ, because that was the first term. So whatever slope you have got, it is by default the net slope, and whatever phase initially that you got, it is by default the net phase. I hope you understood my point. Okay, so finally what I can do is, now I can go on plotting this. Okay, I can go on plotting this. Don't forget the corner frequency. Here the corner frequency. See, if you remember the coefficient of S, the coefficient of S is called as a time constant. Okay, so your time constant is 1 by 5. But if you look at the corner frequency is 5. The corner frequency is 5. So let's see how to go for a Bode plot. So let me just revise what we have written on the previous page, guys. What we have written on the previous page, I'll just write it over here because I need some references here. Okay. For SQ, the slope that I got was how much? It was 20 decibel per decade multiplied by 3. So in a way it was 60 decibel per decade. Okay, 23 is a 60 decibel per decade. and the angle, that is, phase angle that I got is 270 degree, 270 degree. And there are only two terms, guys. So for last term, that is 1 upon 1 plus s by 5 to the whole power 5, but I got slope, that is, I'm interested in net slope, guys. So the net slope was minus 40 decibel per decade, and the net phase angle, that from the previous slide I'm writing, it was minus 180 degree. It is minus 180 degree. So this is the data that I need. So I have written it from the previous page as it is. And henceforth, I'm now going to plot them in the graph. Okay. So let me just plot it in the graph. So what we have on x-axis is omega. This is 0.1. Let me take this is 1. That's the general practice, guys. 10. Okay, not 20, but you can go for 100, obviously. And so on. Okay, but the frequency that I need to highlight over here is not 1, 10, etc. So I have to highlight only corner frequencies. So I'll just keep 1, and rest of the frequencies I'll write corner frequencies. So in our problem, you got only one corner frequency, that is 5. So the corner frequency over here is what? It is 5. So corner frequency is 5. Somewhere over here I'm getting corner frequency 5. For example, somewhere over here I have got 10, and then 100 and so on. Okay. So only one corner frequency is needed. I have plotted only that much. Okay. So initial slope, if you see, it is positive 60 decibel per decade. Positive 60 decibel per decade. So what needs to be done? Always, just follow my steps. Okay. What I'm telling, just follow my steps, guys. What I have over here is, positive 20 decibel, positive 40 decibel, positive 60 decibel, and so on. And over here, I have minus 20 decibel, then minus 40 decibel, minus 60 decibel, and so on. Okay. Now, what needs to be done, guys? Always remember that whenever you want a positive slope, the line grows like this. Obviously, the line which is growing like this having a positive slope. The line which goes down has got a negative slope. I hope you understand that. That's a common sense, guys. So the line which is growing have got a positive slope. The line which is going down has got a negative slope. Okay. So looking at the line, at least you can identify whether it is a positive slope or negative slope, I'm sure. And the line which is, just horizontal line, this is always having slope equal to 0, guys. Please remember those concepts. Okay. The horizontal line have got slope equal to 0. The line which is growing up having a positive slope. The line which goes down has got a negative slope. Okay. So if you see from the start, for S cube, that is a very first term, guys. You have got this positive 60 decibel per decade. Okay. So to have the growing line, obviously, if you want to draw a growing line, the line should start from the bottom. And from exactly which point, guys? Try to remember. If you want positive 60 decibel, start with minus 60. I repeat. If you want to start from positive 60 decibel, start from minus 60. If you want to go for, let's say, positive 40 decibel per decade, start with minus 40. So the starting point, guys, depends upon what is the slope. Okay. And why to choose that point, I'll definitely tell you. You did not to worry about it. Okay. So just for the sake of completing it, let me just go ahead with the logic that I have explained to you, that if you want a positive 60 decibel per decade, you start with a point as minus 60. And then extend this line, which is going through 1. Okay. Why it is so? I'll explain you now. Look at this. Can you see that this line is going up? Okay, please consider my my drawing fault. It's not, even though it is not looking at a straight line, please consider that as a straight line. Else, I'll just rough and I'll make sure that I draw a straight line here. So let me go this way. Okay. So this is 1. So this slope that I'm claiming, okay, it is 60 decibel per decade. Let us understand the meaning of this. Can you see Can you see that? At omega equal to 0.1, please look at this very carefully. At omega equal to 0.1, I'm talking about this. Okay, so what was the value of magnitude, guys? The value of magnitude was minus 60. So the value of magnitude was minus 60 decibel per, okay, minus 60 decibel. Then if you look at this omega equal to 1, if you look at omega equal to 1, so at omega equal to 1, can you see what is the magnitude, guys? So magnitude is, you know, it is 0 decibel. It is 0 decibel. Yes or no? Now try to see the transition, guys. Try to see the transition. So the transition says the previous magnitude was minus 60 decibel. It has increased to 0 decibel. It has increased to 0 decibel. What does that mean? Can I say that the value got increased by the amount positive 60 decibel? The value got increased by the amount positive 60 decibel. Now look at the initial frequency, guys. The initial frequency was 0.1 and the next frequency is 1. So what is the change? What is the exact change? Can I say that it got multiplied by 10? It got multiplied by 10. So can I say that omega is multiplied with 10? When omega is multiplied with 10, your gain is increased by 60 decibel. So can't I say that this is increasing by 60 decibel per decade change in frequency? Per decade change in frequency. That is, initially omega was at 0.1. Now the omega has come to 1. So in a way, I can say that there is a decade change in frequency. There is a decade change in frequency. If you look at the initial point, guys, it is minus 60 decibel. And once you reached at this point, it is becoming 0 decibel. So can't you see that the magnitude is increasing by 60 decibel amount per decade change in frequency? I hope you got that. And of course, if you have doubts, you can definitely ask me. Else, I'll go ahead with my explanation. So you know what? This will continue, guys. This will continue until and unless you encounter this corner frequency. So here, the significance comes of corner frequency, guys. So continue up to corner frequency. Okay. Once you get corner frequency 5, so at this point, your net slope becomes minus 40 decibel. Minus 40 decibel. Now look at that. Come on, guys. It was minus 60 decibel. If it is minus 40 decibel, definitely it has to come down like this. So it is minus 40 decibel per decade. I hope you got that. This is what we call as magnitude plot, guys. This is called as magnitude plot. But let me tell you the reality. The reality is, guys, the reality is that, you know what? For this whole scenario, I did not assume the value of K. Where is K, guys? Come on, guys. K is something called as system gain. Look at this problem. Look at this problem, guys. This is the value of K, guys. This is the value of K, guys. So far, let me tell you, I haven't considered this value of K, which is 0.0032. So let me tell you, when you don't consider K or you ignore K, you by default consider that K is equal to 1. You by default consider K equal to 1. And if you remember, the job of K is to do what? Is to give a shift of 20 log K. I hope you are watching each and every video. If you have watched the previous video, I have made you understand what is meant by, 20 log of K. So 20 log of K is called as a shift in magnitude plot. 20 log of K is a shift in magnitude plot. If this K happens to be 1, guys, 20 log of 1 is 0 decibel. 0 decibel means there would be no shift. But this time, K is not 1, guys. K is not 1. K is 0.0032, guys. Okay. So what is going to happen? So what is going to happen is you will get shift. You will get shift in magnitude plot. Okay. You will get shift in magnitude plot. And that shift in magnitude plot is always 20. I'm sorry. 20 log of K. If you look at K, guys, it is 0.0032. So the shift becomes 20 log of 0.0032. So if you calculate it, you'll get it equal to minus 50 decibel. You get minus 50 decibel. What does that mean is, whatever magnitude plot that you have plotted, guys, you have to shift it. You have to shift it by minus 50 decibel. So let me remind you, what was our previous magnitude plot? Let me just keep it in front of you once again. It looked like this. It looked like this. Let me remind you. It started with the point minus 60 decibel. If you remember, this was 0.1. This is 1. This is corner frequency 5. This is omega. What I have over here is mdb. So it was like that. It was like that, guys. Okay. So you know what? You have to shift the given magnitude plot by minus 50 decibel. Try to understand. If the shift is negative, the plot gets shifted down. If the shift is positive, definitely the plot gets shifted up. What does that mean? What does that mean, guys? You have to shift down. You have to shift down the existing magnitude plot by minus 50 decibel. Effectively, what is going to happen? This point gets shifted by minus 50 decibel down. So the starting point is minus 110 decibel, guys. Minus 110 decibel. So from here, you have to start, plotting your plot. Okay. So what I'll do is we will take, ruler scale and we will draw the exactly parallel plot. We will draw the exact parallel plot. So it may be look like this. So you know what? This is the final plot, guys. This is the final plot. So this is what we call as shift. This is what we call as shift, guys. Okay. This is called as shift. So this is regarding the magnitude plot. Okay. This is regarding the magnitude plot, guys. Let me tell you, we have done with the magnitude plot. What is left is only phase plot. What is left is only phase plot. So what is meant by phase plot? Let us see. So the phase information, I'm sure you have already. Okay. Look at this. Initial phase is minus 270 degree. Look at this. Initial phase is positive 270 degree. And the final phase is minus 180 degree. Minus 180 degree. And this change occurs from corner frequency 5. See, corner frequency is a critical frequency at which the magnitude changes its slope. Similarly, angle also changes. So the point at which the omega's point at which this angle changes, okay, these frequencies are called as corner frequencies. These frequencies are called as corner frequencies. So I'm sure you have no doubts, guys. So what is left? Just a phase plot. Just a phase plot. So let us copy from the previous slide. Let us copy from the previous slide. The initial angle was 270 degree. 270 degree is the initial angle, and at corner frequency 5, the final angle changes to minus 180 degree. So it is very simple to plot now. It is very simple to plot now. So I start with 0.1, then we have got 1, then we have corner frequency 5. Okay, so corner frequency 5 is the point where my angle is going to change, guys. Okay, so 270 degree is the initial angle. Common sense, this is 0 degree, guys. Okay, so 270 degree is somewhere over here. So 270 degree is the initial angle, and this remains 270 degree until and unless we get corner frequency, unless and until we encounter this corner frequency. At corner frequency 5, as you can see that the angle changes to minus 180 degree. So this angle gets changes to minus 180 degree like that. That's it, guys. This is what we call as phase plot. That's what we call as phase plot, guys. Okay, very simple, guys, very simple. Let me remind you once again. Okay, look at this. The initial angle was 270 degree, and at corner frequency 5, the angle changes to minus 180 degree. So let me again plot it over here in front of you. So what we had over here is angle of G of j omega, H of j omega. Okay, so if you look at the initial angle, guys, okay, what is initial angle, guys? Minus 270 degree. That's what I'm talking about. Okay, positive 270 degree, not negative. So 270 degree is somewhere over here. So it remains 270 degree until and unless you encounter a corner frequency 5. At corner frequency 5, if you see the net phase angle is minus 180 degree, so you are going to shift it down and you will say it is minus 180 degree. That's it. This is what we call as phase plot, guys. Okay, so this is how we go for magnitude plot and phase plot. So let's see on the next lecture we can see the more problems, guys. Okay, so thank you so much for watching this video, guys. I'm sure you understood each and every step that I have explained you so far in the Bode plot. So let's go through this quickly, what we have seen so far, guys. Okay, so we started with this Bode plot where I showed you there is two types of plot, that is magnitude plot and the phase plot. The magnitude is always calculated in dBs, okay, and angles are calculated in degrees. The x-axis scale is a non-linear, y-axis scale is said to be linear. Then what we have seen? Okay, then we have seen poles and zeros contribution, guys. Poles and zeros contribution. Please remember, whether they are pole at origin or simple pole, the contribution in the slope is always 20 multiplied by n, where n indicates the repetitions, For example, if that place, if there is only one pole, then it gives you 20 decibel per decade as the contribution. And of course, in the phase angle, it gives you contribution of positive 90 degree multiplied by n. The same thing becomes negative for magnitude and phase when it comes to pole. So pole gives you negative slope contribution and negative phase angle contribution. Every zero contributes positive slope contribution and positive angle contribution, guys. Okay, so try to remember this, and once you understand this, okay, I'm sure you remember in the next problem I have shown you how to arrange them in ascending sequence or the sequence which is required. Okay, so the sequence with which we arrange them is what we called as the ascending sequence of corner frequency. And once we do that, then very well, you have to calculate the slope for that particular pole or zero, the phase for that particular pole and zero, and in the next step you get net slope and net phase. Once you have net phase and net slope, at that corner frequency only you have to change accordingly. Okay, so guys, I'm sure you understood this, guys. Thank you so much for watching this video. Stay tuned to Ekeeda, subscribe to Ekeeda, guys. So myself, Professor Abhishek Barve, I sign out from this lecture. Thank you so much. Bye-bye. Good night. Take care.